So the final thing we're going to look at today is something called Le Chatelier's principle. Le Chatelier is this famous scientist, and he realized that when he's working with different reactions, that if you put stressors into equilibrium, reactions at equilibrium, that the reaction will change. Okay, the reaction will change, and then it will go back into equilibrium. So the whole thing is that reactions are trying to get to equilibrium. That's where they are happiest. And so you can put a stressor and the reaction will shift until it reaches equilibrium again. So Le Chatelier's principle, if one or more factors that affect equilibrium is changed, the position of the equilibrium shifts in the direction that reduces or opposes the change. In other words, this is happening. If something changes in the system at equilibrium, the system is going to respond to relieve that stress. So it's going to shift one direction or the other. So if you do something that affects the product, it might shift to make more reactants. If you do something that affects the reactants, it's going to shift to the product side, depending on what's happening. And so we're going to look at that. So we're going to look at three different stressors. The first being concentration, or the amount of reactant or product. If you add to one side, so you add more reactant, the reaction is going to shift to the other side. So if you add reactant, it's going to shift to the product side, which means your reaction is going to then move or make more product. Okay. If you remove something, so you remove a reactant, then the reaction is going to shift. The product is going to quickly start breaking down so that there will be enough reactant to keep it going. Okay. So it's going to shift to the same side that you removed from. So if you add, the reaction is going to move or be affected on the opposite side. So if you affect the reactants, the product's going to be it's going to shift to the product side. Okay. If you remove, it will shift to the same side. So if you remove the reactants, then your reaction is going to rush to the reactant side to fill in that gap. Okay. So let's take a look at one. So here I have that hydrogen and iodine coming together again. If I were to add H2, okay, if I were to add H2, I'm going to have more reactant than there's product. And so my whole reaction is going to rush or shift to the right to make more product. It's saying, hey, 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 to get back to equilibrium, I got to move to the right to make more product. Okay. If I were to remove some of that I2, okay, my reaction is going to go, whoa, 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 I have a gap. My product is going to start breaking down faster and it's going to shift to the left. That's what we're looking at. So we're just seeing how can I fill in that gap. Okay. So that's the first one. The second one is temperature. Okay. Temperature is really important. Couple of things to remember. Heat is if heat is negative, then it's a product, which means you're losing heat. It's exothermic. If heat is positive, it is a reactant. You're adding heat. It's endothermic. If you add to one side, it's going to shift to the opposite side. So if you add heat to the reactant side, you're going to make more product. Okay. Okay. If you add heat to the product side, you're going to make more reactant. All right. If you remove heat from one side, it's going to affect that same side. So if you remove heat from the reactant side, the reaction is going to slide back towards the reactants. Okay. So let's take a look. So here I have SO2 and oxygen becoming SO3. Okay, if plus heat, it's an exothermic reaction because heat is being lost as a product. So if I were to add more heat to my product side, which means I'm making more product, that product's going to break down and shift to the left and make more reactant. If I add heat, the products are going to start breaking down faster to become a reactant. Okay. Now, sometimes you'll see a setup like this where it'll tell you H is positive, okay? And so you have to understand that if it's positive, it should be on the reactant side, okay? So really it should be N2 plus O2 plus heat makes NO, or nitrous oxide, monoxide. So if I were to move the heat, which is on my reactant side, if I remove it, my products are going to rush in and they're going to make more reactant to kind of help stabilize that. So it's going to shift to the left. Okay. The third thing is pressure. And again, this only works for gases. Pressure only works for gases because pressure has to do with the fact that pressure and volume, and that's why we looked at that whole, we looked at gas laws, how those were impacted. If you add pressure, your reaction is going to shift to the side with fewer moles. So that's different than what we've been looking at, which is like the opposite or the same. You're going to look at the number of moles, or you're going to add up coefficients for all the gases on your reactant side, and you're going to add up all the coefficients for the gases on your product side. And if you add pressure, your reaction is going to shift to the side that has the less number of moles of gases. If you remove pressure, the reaction is going to shift to the side that has more moles. Okay. So, and then if there's equal numbers, so if you add them up and one side has 2 and the other side has 2, then there's no shift at all. You can change the pressure every which way till Sunday, and nothing is going to change the reaction rate. Okay. Again, this only works for gases. You only count the gases. So if you have liquids or solids or aqueous solutions, it doesn't work. It's only if it's a gas. Okay, so let's take a look at one. So I have H2 plus O2 becoming H2O. In this case, they're gases. So if I decrease the pressure, my reaction is going to shift which way? Well, I'm going to count how many gas molecules I have. I have 2 for H2. I have 1 for for O2. So it's 3 on the left, and I have 2 on the right. If I decrease pressure, which means I remove pressure, okay, I should then shift towards my left because I'm going to shift towards the side that has more. So I'm going to shift to the side that has 3 moles. Okay. Let's take a look at this one. Now, don't be thrown because heat's here. Heat doesn't count. We only look at gases. Okay, heat is not a gas. So here I have CO2, which is 1 because there's no coefficient, and I have H2, which is 1. So there's 2 on the left. Okay, and then I have CO. Again, I have 1 right there because there's no coefficient. And then I have another one in water. Okay, my water is a gas. It's in gaseous phase, so it's a water vapor. Okay, and that one has 1. So I have 2 on the left and 2 on the right. So if I decrease pressure, since my moles are the same, there is no shift. I can change the pressure all day and it's not going to affect my reaction rate. So that is Le Chatelier's principle. If you change pressure, temperature, or concentration, you can affect which way your reaction is going to flow and how that happens until equilibrium is reestablished.